My name is John Rivera. I'm working on my senior project with a company named Wasco, and it is on pressure switch lifecycle testing at various environmental conditions. Wasco Sales and Marketing began as a screw company and eventually evolved into a manufacturer of pressure and vacuum switches, transducers, and transmittals. Created and maintained by the Way family, the company's name is an acronym for Way Automatic Screw Company. Today, Wasco supplies the fire suppression, medical, semiconductor, and defense markets in addition to providing solutions for industrial applications such as automation. Today, environmental test chambers are used in various engineering industries to test the effects of specified environmental conditions on biological items, industrial products, materials, and electronic devices and components. An environmental test chamber artificially replicates the conditions under which machinery, materials, devices, or components might be exposed to. It is also used to accelerate the effects of exposure to the environment many times at conditions not actually expected. Wasco uses chambers like these to test the quality requirements of the products. Wasco has been recently working to develop a new product line named Project Semi for a leading supplier of wafer fabrication equipment, Lam Research. In 2013, Wasco upgraded their environmental testing chamber with the purchase of an S-Spec Plantonius series environmental chamber with the intention of testing Project Semi switches. This report is going to outline the process of developing a high-speed test and measurement system for automatic simultaneous data acquisition of semiconductors, actuation pressure in a controlled environmental chamber. The purpose of this particular environmental test is to validate that Wasco switches perform to the quality standards specified in their product catalog. The system will be designed to test the new product line, Project Semi, as well as be used in the place of older procedures for all other product lines. As far as the agenda goes for the rest of this presentation, we will be looking at the problem statement, the project scope, the objectives and deliverables, the success factors, the systematic approach to the project, the milestones, the risk management plan, and the current status of the project. Problem statement. Since the creation of the new project line, Project Semi, Wasco has not been able to establish a new system to test this product line. Currently, they are using an obsolete environmental testing procedure using a Tenney Junior environmental testing chamber, as you can see pictured at the bottom right. Due to its size and speed, it is limited to testing only a few products very slowly. Presently, the system is very slow, unreliable, and incompatible for all products. In addition to that, Wasco is seeing a high rate of returns due to the lack of quality assurance with their new products. There are four main activities that fall within the project scope. The first being to develop a high-speed test and measurement system with the following functionalities: lifecycle testing, environmental testing, accuracy and repeatability testing. Second, we are going to use data acquisition to test the actuation pressure of between 50 and 100 pressure switches. Then that data is going to be pushed to a storage database in real time. In addition to that, we will be designing an ergonomic server rack that will house all the necessary hardware to use for testing. Objectives. These are the criteria for success of the project. The first one being is to design the system using a state machine. The second is to monitor and control the following through LabVIEW: the S-Spec environmental chamber, the Menso pressure controller, which is pictured at the top right. This will be used to test switches between 0 and 100 psi. The Hosker AG series gas booster. This will be used to test pressure switches beyond 100 psi up to 1500 psi. The NI DAC device, the solenoid valves, and finally, be able to use real-time data collection using Microsoft Access and LabVIEW integration. Deliverables. These are what are going to be produced at the end of the project. The first one being a high-speed test and measurement system using NI LabVIEW software. The software will be able to have the following functionalities: lifecycle testing, environmental testing, accuracy and repeatability testing, and be able to automatically push data to an Access database using data acquisition of the pressure switches. And in addition to that, we will be making an ergonomic server rack that houses all the necessary hardware for the project. Success factors. These are the elements that are key to the success of the project. The first and most important one is to have satisfied clients. We want to ensure that Wasco is satisfied with the end product. Following, we want to meet the project objectives and deliverables in an on-time manner. The success of this project will provide Wasco more opportunities to satisfy customers who require similar environmental testing procedures. The program will also enable Wasco to run lifecycle testing, accuracy testing, repeatability testing, and further prototype testing in the future. The project is projected to expand Wasco's customer base and grow the company as a whole. Project team roles and responsibilities. At the top of the chain, we have John Warren, the Chief Design Engineer. He is responsible for creating the user requirements of this project. Underneath John Warren, we have myself, the Project Manager. I am responsible to make sure the project meets its objectives and deliverables and that the project is finished on time. Underneath me, we have Caleb Baker, Steve Yocko, and John Jackson. Caleb Baker will be a key factor in creating the requirements for the database. Steve Yocko is in charge of designing the manifold that will house the pressure switches, while John Jackson will be responsible for creating any additional hardware that is needed for the project. Wasco operates using the crawl, walk, run methodology. In the crawl phase, the changes are immediate, with immediate benefits. They can be implemented easily down the road and lay the groundwork for bigger, more impactful changes. These also include configuring lower-level programs that work independently from one another. In the walk phase, the changes are near-term. They have a longer time frame than the crawl changes. These may include process changes, minor hardware/software upgrades, or consolidating various aspects of the crawl phase into a larger framework. In the run phase, the changes are long-term. These changes may include database implementation or organizational restructure or adoption of data devices. In this sequential methodology, you must crawl before you can walk, and you must walk before you can run. Within the system, DMAIC methodology can be applied at the various phases. However, contrary to the traditional approach, DMAIC methodology is structured differently when using code. In the define stage, the software developer begins his work by reviewing and understanding the design and requirement specification documents. These documents are essential for understanding the user requirements and creating a framework for the software code. In the measure stage, we will be using an older environmental chamber to test the current baselines for improvements. This will be the performance metric to compare to at the conclusion of the project. In addition, we will be using a low-level process flow baseline for the code. Analyze. In the case the software development team is unable to understand user requirements correctly and further clarification is required, the deliverables are sent back to the user. In addition, the software development team also returns the requirements that are understood by them. Improve. After the requirements are clearly understood, the design and specifications are implemented in the source code, which would be the main VIs, the supporting files, which would be the sub-VIs, and the project library. In some cases, there may be a proposal of change in hardware or software specifications for program optimization. And finally, control. Software testing is carried out to detect and correct errors on each module and sub-VI of the software code. We will be using a work breakdown structure of 5 procedures to finish this project: initiation, planning, execution, control, and closeout. Project schedule and milestones. The first step of the project is initiation and includes evaluation recommendations to develop the project charter, to develop the deliverables, and to find a project advisor and review the project charter with Wasco. This was finished on December 29th. The next step was planning. This included to create a preliminary scope statement, develop the project plan, and get it submitted for approval. This was finished on January 26th. The next step was execution. I will be getting into this more on the next slide, but it is due June 6th. Following that, we have control. This includes to have project status meetings throughout the duration of the project and to develop the risk management plan. Finally, we have the closeout. This includes the audit of the project, documenting the lessons learned, updating the files and records for Wasco, and gaining formal acceptance of the project. Breakdown of execution. The execution phase is the biggest part of the project, beginning with validation of the user requirements. This includes validating everything needed for the LabVIEW program and the server rack. Next, we have designing the system. This is where we will be using blueprints to create everything needed for the scope of the project. Following that, we have procure the hardware and software. Here, we will be acquiring all the software and hardware, including the DAC devices, the Mental Pressure Controller, the SPEC changer, the relays, the switches, the pneumatic plumbing, and the transducers. Following that, we have install the development system. Here, we will connect all components to the server rack, set up the computer, set up the plumbing into the SPEC environmental chamber, and connect all the electrical switches to the PLC and DAC devices. Following that, we have the testing phase. This is where we will test the program with a low number of cycles ramping through various temperature settings. Following that, we have install the live system. This is where we make the final ergonomic adjustment to the server rack and clean up and label all the electrical components. Next, we have user training. This is where we will work in conjunction with the quality department to get all personnel up to date on the new software. Finally, in the go live stage, here we will make minor continuous improvements to the program. Risk management plan. This is a breakdown of the 3 main risks and their contingency plan. The first risk being we are unable to use a database within the system. This has a low probability but a high impact and falls on the project manager. The contingency plan is to store the data on a local drive such as an Excel file or PDF file. The next risk is that the program runs too slow testing 100 switches. This has a medium probability and a medium impact and also falls on the project manager. However, we will be able to scale the system and limit it for optimal speed. The final risk is that the program crashes when communicating with the environmental chamber over a TCP connection. A TCP connection is an Ethernet connection and is done over the internet. The probability of this is very low but has an extremely high impact and also falls on the project manager. In the case of this, we will redesign the system to communicate through a GPIP connection, which is a solid connection. Quality management and performance measures. To maintain direction and ensure the success of the project, bi-weekly updates will be held with the Chief Design Engineer John Warren and the Quality Engineer Caleb Baker at Wasco, in addition to weekly updates with the Project Academic Advisor Roya Javidpur. To maintain the schedule, we will be closely looking at the Gantt chart and staying on track with it. In the case that we are not able to finish the project in time, we have agreed on minor changes to the project scope. Current status. As of March 2nd, we have a prototype built for the project. It is built using a state machine with 7 states. The first state is the initialized vent. This is used to release any pressure that has built up in the manifold over time. Following that state, we move into the idle stage. This is where the program sits in idle until the operator hits the start button. This state is also used to set all the base requirements for the test, such as the upper set point pressure, the lower set point pressure, the temperature and humidity, and the total number of cycles. Following that, we go to set the temperature and humidity. Then, moving on, we wait for the temperature and humidity to be achieved. The temperature and humidity are given a tolerance, so the runtime for this cycle can be decreased. After we achieve the target temperature and humidity, we move on to the pressurized stage. Here, the manifold will increase in pressure until we hit the upper set point pressure. Then we will move on to the vent stage. In this stage, the system will vent out pressure until we hit the lower set point pressure. Then we move on to the cycle count. Here we see if the cycle count has been achieved. If not, we move back into pressure and complete the cycle until it has been achieved. In addition, I've created a refresh settings button. With this button, the program is able to jump from any state back to setting the temperature and humidity and then jumping back into the pressurized. This is helpful if the operator wanted to change the temperature or humidity in the middle of a test. Appendix.